Our topic for this week is going to be stellar evolution, but before we can understand that, we have to learn about how we measure the masses of stars. So let's go back to our HR diagram and how many stars there are in each region of the HR diagram. So here we have the Hertzsprung-Russell diagram. We have temperature or stellar class on this axis. We have brightness or visual magnitude on this axis, and you can see there's many more red main sequence stars, and as we go up the main sequence there's less and less. And there are very few up here and very few down here, and any understanding of stars has to explain this distribution. And so we've got the faint stars, the hot bright stars, and then the giants and supergiants. So what about these stellar masses? Well, originally the HR diagram was just literally, I know how bright it is, I know what the temperature is, I can plot it, and we get that particular distribution. But later it was discovered that the main sequence was really a mass sequence. And it turns out that mass is the most important thing when we want to understand the evolution of stars. So, how do we determine the masses of stars? Well, how do we determine the masses of planets in the solar system? We did this, and we worked out the mass of the Sun before. We do it by observing orbital motions. So, moons orbit according to Kepler's laws, and in fact the planets orbit the Sun according to Kepler's laws. And that's how we got the mass of the Sun. But for other stars, planets are difficult to detect, let alone watch for this purpose. And in fact, we're detecting planets by using this mechanism. But stars also come in binary systems. In fact, about 48% of stars are single lone stars, and about the same amount, 48%, are in binaries, and the other 4% are in multiple systems. And so we can use that, and eventually we find that the low mass stars are at the red end of the main sequence, and the highest mass stars are at the blue end. But I digress. So let's go back to Kepler's third law. We have, for the solar system, in years and AU, we get the mass in solar masses. Now, actually this works even without the, even if it's not in the solar system. This is basically the conversion factor. We have to work in years and AU, and then we get the mass in solar masses. Remember we calculated, actually derived this equation. So if we've got a binary system and we work in these units, it turns out that 4 pi squared over g is 1 in solar units. And so it simplifies, and we get p squared equals a cubed over the masses of the two stars, where my stars are A and B. And remember, this is in solar units. So I can say, if I can watch them and work out what the semi-major axis is of their orbits and the period of their orbits, then I can work out what the total mass is. So just by simply looking at their separation, remember we did this before, A was the separation of the two, we can get their combined masses. So here we can watch what this actually looks like. So we've got two stars and they're orbiting the center of mass. They get closer and further away from the center of mass. They have elliptical orbits, so you get them moving faster when they're closer and slower when they're moving further apart. But they always have the same periods, just like we had before. Let's just watch that one more time. And so we can watch these things, and we can determine from their mutual motions where the center of gravity is. And if we can work out where the center of gravity is, then we've also got the distance of the individual stars from the center of mass, and that allows us to do more than just get the total mass. So we can work out both their individual masses and their total mass. So remember we did this before when we derived that equation that MA over RA equals MB over RB. And so we can just rearrange that, so we have masses on one side and radius of orbit on the other. And we also know that MA plus MB is M total, which is what we get from using Kepler's third law. And if that's true, and we also know that MA over MB is RB over RA, then we can substitute this into, so now we've got MA in terms of MB, and we can substitute that into this equation here. So now we know, if we know what the radius of each orbital motion is, then we can determine from the total mass what the individual masses are. Okay? And you only need to get one, and then you get the other one just simply by the difference. So let's do an example of this. I've got MA-RA equals MB-RB, and I've rearranged that. And now let's say we've used the period and the separation of the stars, and we find that their total mass is 2 solar masses. And we know from where the center of mass is that the ratio of MA over MB is going to be 2. This is something that we can also determine. And so what we get is that MA equals 2 MB, just rearranging that. And so we can then put MA in here as 2 MB. And so now we get that 3 MB equals 2 solar masses. So now we know what MB is in solar masses. And now we know what MA is in solar masses because MA is 2 MB. And so simply by observing these, we can work out what the masses of the mutual parts are. Okay, so if we've got binary systems, we can work out what the masses of the stars are, and then we can put that on our HR diagram. And so, but to do what we just talked about, they have to be resolved. They have to be far enough apart in the sky that we can see them moving. Some stars are not far enough apart, or their inclination of the orbit is such that we don't see it. And in that case, you need to use the either spectroscopic binaries or eclipsing binaries. And we're going to talk about those next. So for spectroscopic binaries, here I have a system. So I have a center of gravity, I have a star A that's going around in its elliptical orbit, and I have a star B that's going around in its elliptical orbit. And what happens is that when A is moving in this direction, then its spectral lines are going to be blue shifted because it's moving towards us. I have this down here. At the same time, B is going to be moving that way, so it's red shifted. But then a little later, you're going to have B moving this way and A moving this way. Neither of them is shifted. And then when A gets to here, it's going to have red shifted lines, and this one's going to have blue shifted lines. And so by watching how, even though we might not see two separate stars, we can see how the lines change over time, and from that we can derive their properties. How do we actually get this? Well, it's just the Doppler effect. And so what you see is something like this. Actually, what I'm going to try to show you is this in an animation that for some reason I couldn't embed in the PowerPoint. So here you can see it. I've got star A, it's going around here. If we watch this one, it's going this way, and we can see that it's got it's at rest because it's not moving away from us. Now it's moving away from us, so it's blue, it's red shifted. Now it's moving this way again, so now it's blue shifted. And all the while, the B lines are doing the opposite thing. If we take this spectrum over time, we can then work out the radial velocity, and we can see that the B lines are moving this way when the A lines are moving this way. And you can see from the shape here that you actually get the eccentricity as well. So you can learn a lot by looking at the spectrum over time, and you can determine what the spectral parameters are. So let's go back to our PowerPoint. Okay, so now we can do that with spectroscopy. We also have eclipsing binaries. So if you think about, I've got a system here, I've got a blue star and a yellow star, and when the yellow star goes in front of the blue star, it blocks the light from the blue star, but it doesn't block it completely. So we don't go down to zero light, but we lose some light, and so we get this dip in the brightness. And then we have both stars are visible, and then we have the yellow star going behind the blue star, but it's also not completely eclipsed. And remember, a yellow star per unit surface area produces less light, and so when it is eclipsed, you don't see as big a dip. The dip is not as deep. And then back to here, we've got no loss of light, and then we're back to having the yellow star blocking. And so you can see from that, you can determine the period, and you can also from these dips work out how much light is missing, so you can work out the inclination of the orbit. Here we have another system where we have a blue star and a red star, and the red star is much bigger, and so the red star completely blocks out the blue star and we lose a lot of light, whereas the blue star only blocks a tiny bit of the red star, so we don't lose that much light, and so we get a difference in the brightness there. And so this allows us again to work out what is the period of the orbit, and we can also put limits on. In both cases, we can put limits on the size of the orbit because we can't resolve them, we can't see them as separate stars. And so this allows us to determine some things about the objects. And so by looking at, remember, 48% of stars are in binary systems, and so we've got lots to play with, and so we find that the main sequence really is this mass sequence. So now we're actually going to plot them together. So we've got the mass of the star versus the luminosity. So this is still the luminosity, but instead of having the temperature on here, we've got the mass on here. And this is obviously a log-log scale. You look at the scale, it's clearly not linear. And you get a straight line, more or less, in log-log scale. And what it shows, obviously, is that main sequence stars have greater luminosity when they have greater mass. And if we look at that log-log plot and fit a line through that log-log plot, we can work out what the power law is. And it turns out that it's more or less L goes as m to the 3.5, which means that, you know, if you've got a star that is twice as bright, twice the mass, it'll be 10 times as bright. And if you've got a star that's 10 times the mass, it will be 3,000 times as bright, and so on. So what effect does this have on a star's life expectancy? Well, let's consider an O star, an O-type star, which is very hot, 30,000 Kelvin. It's 10 times as hot as an M star, which is only 3,000 Kelvin. An O star is 10 to the 4 times as bright as an M star. Remember, an M star is fainter than a sun-like star. But an M star only has 14 times the mass. Well, what does that mean? Well, the O star has to be burning hydrogen. It has to be doing fusion 10 to the 4 times as fast to be 10 to the 4 times as bright, right? It has to do 10 to the 4 times as many reactions every second to be that bright compared to the M star. And so, but it only has 14 times as much mass, so it only has 14 times as much fuel. And so it will run out of hydrogen much faster. So an O star will evolve much faster than an M star. And you'll remember that this came up when we looked at clusters, when we were talking about main sequence fitting. Okay, so here we have a HR diagram again, and here we have the different masses put on. So we've got the solar mass in solar masses, low masses at the red end, high masses at the blue end. And so remember that it basically goes as luminosity goes as mass to 3.5, and lifetime is proportional to the mass over the luminosity. So the mass gives you how much fuel you've got, and the luminosity tells you how fast you're using it. And so, but if the luminosity goes as m to 3.5, you can get rid of that one. And so it means that the lifetime is inversely proportional to the mass, but to the power 2.5. And so we can get a feel for, we know the sun has a lifetime of about 10 billion years on the main sequence. If you have one that's 10 times as massive, it'll only last for 30 million years. It's a lot slower, a lot shorter life. And then a tenth of a solar mass will last 3 trillion years. Now, one thing to emphasize is that this mass-luminosity relationship only holds for main sequence stars. If we look at stars that are not main sequence, this doesn't work. So in general, supergiants are more massive than giant stars, but even then there's some overlap. And supergiants are generally 10 solar masses and above, and giants are generally less than about 8 solar masses. And there's a grey area in between, which we can talk about at some point. The maximum mass for stars is going to be somewhere in the 50 to 100 solar mass range, and the minimum mass is down at about 0.8. And I'm just going to explain why those limits exist. So if you have a protostar that's, you know, more than about 200 solar masses, it can't get to the main sequence. It collapses so fast and gets so hot that it explodes. It basically it cannot survive at all. It never gets to stable hydrostatic equilibrium with fusion. Whereas if you've got a low mass star below about 0.8 solar masses, it just doesn't ever get to the point of being able to do hydrogen burning, and we call those stars brown dwarfs. And that's it for stellar masses. Next we'll get on to looking at stellar evolution in earnest.